Hey guys, right now what we're going to get into is some more kinematics. This is an interesting topic in the physics curriculum, and personally it's one of the most challenging topics for me because it's not so much you've got a concept and here's a law and now you apply it and you have this beautiful model of the situation. It's just there's so many different things that can happen, and as we continue I really hope that you see that. So let's begin, and I brought my friend Bobby J to assist us, and Bobby J is impervious to all forms of damage, so let's assume that he has all 5 Infinity Stones. So Bobby J wants to take his new BMW Mini Cooper for a spin. While traveling at 85 kilometers per hour, he collides with a tree, and the front end of the car compresses. He travels zero point 0.8 meters during the collision. What was his average acceleration during this collision in G's? Now, before we get to the last part, let's stop. Let's take a moment. Let's look at the situation. Bobby J, he's coming down a bend, maybe he's going down a straight road, and he's traveling at 85 kilometers per hour. And through some unfortunate chain of events, he collides with a tree. And the moment that we're concerned about is the instant that he connects with the tree to the instant that he travels 0.8 meters. Okay? So if we were to look at this, we could maybe use this as we could represent Bobby J as a point object. And this is him inside the car. This is from the frame of reference of inside the car. And what happens is he travels some distance. And bear in mind, Bobby J is inside the car, so he is also moving at 85 kilometers per hour. So this is the distance that he travels during this collision. We're going to assume that after he travels this distance, he comes to a complete stop. Okay? So his initial velocity here, and one quick thing. Whenever you have kilometers per hour and you want to take it to meters per second, you can multiply it by this conversion factor of 0.2778. And if we were to multiply 85 by 0.2778, we get 23.6 meters per second. So in terms of meters per second, this is Bobby J's initial velocity. This is his velocity the moment that he collides with the tree, okay? And we're not concerned with the moment he collides with the tree and he kind of slows down. We're looking at the instant before he connects with this tree. And that's where we're going to be taking our reference point from. And his velocity, his initial velocity at that point is 23.6 meters per second. And we know his final velocity because he comes to a complete stop after this collision. He travels this distance and he comes to a complete stop. So his final velocity is 0. So we have a few things. We have, and we're going to take this point as x naught. We're going to take this point as x. So our change in displacement will just be final minus initial, which will just be this 0.8 meters. And I think we're ready to actually begin to solve this. And if you remember the equations that I had written up there, our variables align with this equation right here, because they asked us what was his average acceleration during this collision. And during this question, we're assuming that acceleration is constant, okay? So we have our final velocity, we have our initial velocity, we have our change in displacement, and we want to find an acceleration. So from here, we know our final velocity is 0. We know our initial velocity is 23.6 squared plus 2 times acceleration in the x. I just like to put everything in brackets so it's nice and clean when I'm taking things over. And now I'm going to subtract a negative 23.6 all squared from both sides of this equation. And over here, 23.6 all squared minus 23.6 all squared is 0 times 2 times acceleration in the x times 0.8. So acceleration in the x is equal to negative 23.6 squared divided by 2 times 0.8. And this gives us a whopping 348.49 meters per second squared. And the negative denotes the direction. In this question, we're assuming to the right is positive, and we assume to the left was negative. And if we assume to the left was positive and to the right was negative, we would have had to have made the appropriate adjustments because the velocity is now going to the right, which is negative. So there would have been a few adjustments, but generally by convention, most persons use to the right as positive and to the left as negative. But this is his acceleration, his average acceleration during that 0.8 meter movement. But they asked us to find his average acceleration in G's. And when they ask you to find something in G's, they're just asking you to figure out what is this acceleration in terms of the gravity. And our gravity is equal to 9.8 meters per second. Okay, ran out of space there. Squared. And this is just the magnitude. This is the magnitude of the gravity, okay? And I want this answer, I want the units here to be G, okay? So what I'm going to do is I'm going to multiply by 1, okay? So that's minus 348.49 meters per second squared times G over G. Because G over G, I'm treating that as a variable. G over G is now just 1. I haven't done anything new, okay? So over here, and I want G to be the unit in the numerator. So I have minus 348.49 meters per second squared times G divided by 9.81 meters per second squared, because I want to keep this G up here and I want to remove these units. So this cancels with this, and I end up with 35.52 G. And we want to interpret this answer. So just ignoring the negative, ignoring the direction, let's look at the magnitude of this acceleration. This is saying that Bobby J is undergoing 35.52 times the force of gravity. And just for reference purposes, the average person can survive 5 times the the acceleration due to gravity. And there have been cases of people surviving even higher amounts than this, up to 40 Gs plus. But these are professional fighter jet pilots, and the amount of time that they experience this has only been momentary. So luckily, like we said, Bobby J is immune to all forms of damages, so he comes out A-okay. Nonetheless, an important part of the question is to really make these fundamental assumptions that I'm looking at the instant right before I hit this tree. I'm looking at this instant right here before I hit that tree. And that is my velocity, because we're also assuming that this velocity, he's traveling this constant velocity, or maybe this is the velocity that he hits right before he gets to the tree. But this is what we're concerned about, his initial velocity right before he hits the tree. And we also know we have to assume that after he travels this distance, he comes to a stop. That's what we're concerned about as well. And once we have this situation inside our head and we have it drawn out, things become a whole lot easier in terms of our calculations, because this is something that could be done in one line. And as you practice and you become more comfortable, you'll begin to see the physics more. And once you can see the physics, it becomes so much less intimidating. Okay, so thank you for watching. If you're here right now, give yourselves a round of applause, because it means that you're interested in learning, or maybe you've made a mistake, or maybe you're just curious. Regardless of the situation, you're amazing, and I hope that you found this helpful. And Bobby J thanks you too.